let us talk about use of kernel drivers by Windows malware. So why does malware try to access the kernel? If a malware is able to access the kernel, it can control almost everything and execute with full privileges. Malwares can do the following once they have access to the kernel. They can kill antivirus and EDR processes in user mode. They can install rootkits in order to hide their own processes, files, and network communications. Let us talk about different ways by which a malware can access the kernel. So one way is to install a new kernel driver. Another way is to exploit existing kernel drivers. Here are a few challenges while performing the above two tasks. In order to install a kernel driver, the driver is required to be signed, which can be often challenging for malware authors. And if the malware authors want to exploit an existing driver in the kernel, it can also be tough in case the driver is patched. And it can also happen the driver might not be present in the system in case if it is a non-Microsoft or third-party driver. So here are some of the new techniques employed by malwares today to access the kernel. So one way is install a signed driver of legitimate programs which have capabilities like killing processes and do other stuff. So such drivers can be found with tools like Process Explorer and Process Hacker, which have capability to kill processes and do some other stuff. Another method is installed a signed driver, but with some vulnerability, and then exploit the driver in order to gain higher privileges. So this technique is known as bring your own vulnerable driver, or BYOVD. Malware can have these drivers embedded in them for the purpose. So they can have this driver in the resource, or they can have these embedded somewhere in the file, in their own file. Once they get access to the kernel, they can do many things like killing of EDRs or antivirus processes. So let us talk about some basics of kernel drivers. So we'll talk about the basics so that you'll get some basic understanding of how the malwares can misuse it and various components of kernel drivers. So what is a driver? So let us talk about something known as a device driver. A device driver is a program that can directly interact with the hardware. Drivers can be layered as well. In this image, you can see there is a device and there is a user mode code, which is in the user mode part of the virtual memory. And there are low-level drivers which can interact with the hardware, or these are known as the device drivers, which can directly interact with the hardware. There can be higher level drivers which can take input from the user mode code. So there can be multiple drivers instead of just only two. So the top level drivers send information to the lower drivers, and finally the information is received by the lowest driver, which is the device driver. So there can be drivers which may not be associated with real devices. For an example, a malware which install a rootkit driver did not be associated with any of the hardware devices. So before that, let us look into some basic of how driver code is written. So this is a framework of a basic driver code on Windows. So every driver program has something known as driver entry, which is equivalent to main program in C or C++. So the driver entry has a parameter, the first parameter, which is the driver object. Next, there is a call to API known as IOCreateDevice inside the driver entry. So this API creates a device object. So the device object is created by using a device name, and the device object is basically pointed by the driver object. So the driver object has a pointer to the device object. The next API that can be called from inside the driver entry is IO create symbolic link. So this API creates a symbolic link for the device object. So with the help of the symbolic link, this device object can be accessed from the user mode just like any other normal file. So from user mode, this can be treated as a file. Next is this part of the code, which looks like driver object has something known as major functions, and these are generally known as the dispatch routines. So this code creates the dispatch routines for the driver object. Now, how does the dispatch routines look like? So dispatch routines are part of the driver object, and the dispatch routines point to the functions like irpmj underscore create may point to a function which can be implemented by the programmer, and the name of the function is create. Remember, this name create is provided by the programmer. So the programmer can put any name here. Next is irpmj read, and the corresponding function to that is read. So again, read can be any name. Similarly for write, similarly for close, and similarly for irpmj device control. So the function that is associated with the dispatch routine irpmj device control looks like this. The function has a switch case statement. So we'll look into this, what this switch case statement is used for. So before that, we'll look into how the drivers can be installed. So the previous code can be compiled into a sys file. So the code which I showed is not complete, but if you compile any of the driver code, a sys file is created, and it can be loaded into the kernel as a service. So malwares usually install the sys file driver as a service, just like a service. And the sys file is installed in the kernel as a kernel module. The service APIs which are used to install the sys file to the system are OpenSC Manager, which can be used to open the service manager, create service, which can be used to create a service from the driver file, and start service can be used to start the driver code. So here's the code which can be used to install a sys file. So here is the create service API, and the 8 parameter to the create file API has the name of the device driver file, of the driver file, which requires to be installed. So next is, how are the functions in the driver called? We saw that the driver code has many functions like driver entry, and after that, your dispatch routines are there. So we need to know when they are called. So when a driver is installed or loaded in the memory as a memory module or a kernel module, the driver entry is called. But when are the dispatch routines called? RPMJ create, RPMJ read, RPMJ device control, how are they called and when are they called? We need to understand this because, say suppose if you want to debug a kernel driver, the understanding of when these functions are called is very important. So let us discuss about how dispatch routines are called. So the driver object has the dispatch pointers to the dispatch routines. So whenever you want to call something inside the driver, you need to use create file API with the parameter as symbolic name to the device object, and the create file uh, the create file invokes the function associated with the rpmj create dispatch routine. And after the create file is executed, a file handle is returned, and that file handle can be used on the APIs like write file, read file in order to communicate with the driver. So next, when the write file is called with the parameter as file handle, which is derived from the create file, the the code which is associated with rpmj write dispatch routine is invoked. Similarly, this will happen for the rpmj read as well. So if read file is called using the f handle, then the dispatch routine associated with uh, rpmj read is invoked. Now, when device IO control API is used with parameter as file handle, there is a function associated with rpmj device control. That function is invoked. If you look into this function, it has switch case statements. So we'll look into how this things works. So IOCTL and device IO control API. So what are IOCTL? IOCTL's full form is input, output, or IO control code. IOCTL is the message sent from kernel to user space. Device IO control API can be used to send and receive message to and from the kernel using the IOCTL code. So here is the API device IO control. For more details, you can refer to MSTN. So the first parameter is the handle to the device, which is uh, returned from the create file API. The next parameter is device IO control. So device IO control, this is the IOCTL code which can be sent to the device. Next is the buffer. So this buffer can be used to send data to the driver, which is in the kernel mode. So using this, the data can be sent from the user mode to the kernel mode. Then is the IO output buffer. So this is the data that is returned from the driver to the user mode. So here is how the device control API works. So device IO control API takes the first parameter as the handle to the device object, and then the next parameter is the IOCTL code, which we showed in the previous slide. So whenever this particular API is called, the function associated with rp underscore mj underscore device control is invoked. So this is the function that is invoked. Now, there is a switch statement here, which takes the parameter, which is the control code. Say suppose your IOCTL code is IOCTL underscore code underscore 1. So there is a case statement which sees that the IOCTL code is IOCTL underscore code underscore 1. So it executes the code which is under this case statement, that is the function underscore 1. Similarly, if IOCTL underscore code underscore 2 is passed on using device IO control, then this particular function is executed, which is under the case IOCTL underscore code underscore 2. Next is IOCTL underscore code underscore 3. So this one is invoked when IOCTL underscore code underscore 3 is used in device IO control. Now we'll talk about a concept known as IRP. So IRP stands for Input Output Request Packet. It is a kernel data structure. IRP carries IO request in the kernel from one driver to another. You can say IRP is generated in response to the IOCTL code that is sent from the user application. The IRP holds the IOCTL code and other information required to process a request. So IOCTL exists both in user and kernel mode, while IRP exists only in kernel. So here is how the IRP is created. Say suppose the device IO control uses the IOCTL underscore code underscore XYZ as a IO control code. So this one is passed on to the IO manager, which is in the kernel, and IO manager in response to the device IO control creates a IRP packet, which has the IOCTL code and other information in it, and then sends it to the driver object. So now we understood basically how the IOCTL works and how the IRP works. Now let us come to how the latest BYOVD malware works. So malware installs a kernel driver. User mode parts uses IOCTL to communicate with the kernel driver. If a driver has a IRP function, if a driver has a dispatch function in order to kill a process, user mode code sends a corresponding IOCTL, which can ask the kernel driver to kill a user mode process, which can belong to a EDR or AV process. If a driver has a vulnerability in a function, the exploit buffer can be passed onto the kernel using IOCTL, which can further exploit it in order to gain control of the system. So if you want to learn more about kernel debugging and learn about kernel malwares, then join my training, Advanced Malware Reverse Engineering.